Welcome to Mrs. Z's Chemistry. In this video, we'll be doing lots of practice problems with unit conversions. I suggest you get out a piece of paper, your calculator, and keep your periodic table handy as well. We will use something called dimensional analysis, or the factor label method, to convert units. A unit conversion is a ratio of two quantities that are equal to each other, but have different units. In order to solve problems with dimensional analysis, we're going to start with the quantity given in the problem that is not equivalent to another quantity. In other words, it's not a unit conversion, and it's the one that needs to be converted. Looking at our periodic table for the unit conversions, we can see we actually don't have one unit conversion between inches and millimeters. If you happen to have that memorized, go for it and go ahead and use it to convert 13.51 inches to millimeters. Otherwise, we'll need to do this problem in two different unit conversions. So first we can find something inches to centimeters. That would be an English conversion. We could use this one, inches to centimeters, or this one. I'm more familiar with the one on the bottom here, the 2.54 centimeters equals 1 inch. So then once we get to centimeters, then we can go from centimeters, which is right here, to millimeters. That is a difference, the 10 to the negative 2 and 10 to the negative 3. That's just a difference of 10. That means there are 10 millimeters, the smaller one, in 1 centimeter, which is the larger one. So we can set it up this way. We're going to start with the one that we are given, the 13.51, because 13.51 is not a unit conversion. It is the one we need to convert. We're going to open up a parentheses here and write in a unit conversion. We're going to want to put inches on bottom and centimeters on top. And that's because we want our units to cancel. Units can only cancel when one is in the numerator and the other one is in the denominator. From the unit conversion on the back of your periodic table, it said we had 1 inch is equal to 2.54 centimeters. So we could stop here, pull out our calculator, multiply 13.51 times 2.54, but instead let's just open up the next set of parentheses and write out the next one. Centimeters on bottom and millimeters on top now. This is because we want to cancel our centimeters, numerator and denominator. For every 1 centimeter, we have 10 millimeters. So we're going to multiply. There's imagine little multiplication symbols in between each and every one here, or just put these all in parentheses. Remember, with math, if you put everything in parentheses, then you're going to multiply all of them. So you're going to take out your calculator and you're going to multiply 13.51 times 2.54 times 10, and we'd get just the unrounded numbers 343.154. So here is the setup all typed out here. You can set up the work as parentheses around each unit conversion like we just did, or you can imagine just straightening the parentheses lines into just one line between each unit conversion like this here that I have written out. I call this a train track because it kind of looks like a train track, and you can set it up either way, either train track or parentheses. The important part is that we are doing the same thing either way. We're setting up unit conversions so that the units cancel. We are making sure to include the units in our work and then actually drawing the line through the units. Then we know that we multiply the numbers across the top and divide the numbers across the bottom. When we are deciding how many significant figures or sig figs to round to, we only look at the measured number in the problem. The 13.51, that is the measured number. Someone measured something with a ruler and it came out to 13.51. We know that the 1, as the last digit here, is the estimated digit. So we know the tick marks measured to the tenths of the inch, and then we needed to estimate one more number in between the tick marks. So the 13.51 is the measured number, and for significant figures, we only look at the measured numbers. We don't care about the unit conversions because those are exact or counted numbers. So that means our answer should match the same number of significant figures as the measured number. So that's why, to round this to the correct or appropriate significant figures, we would round it to 4 sig figs, which would be to this is the 4th digit, and your 5 rounds that 1 up to a 2. So our answer to correct significant figures is 343.3 millimeters. So I'll say that again. However many significant figures were in the measured quantity, that's how many significant figures our answer should have. If you ever have more than one measured number in your problem, which often we do, and then we multiply them or divide them or whatever, and if they have the 2 different numbers of significant figures, say one has 4, the other one only has 3 sig figs, then your answer should be rounded to the one with the least amount of significant figures. This problem is converting grams to micrograms. This little symbol, this little U with a funky little tail, that is a Greek letter, and it means micro in this case. So this is all within the metric system. So let's go to the periodic table, find our metric system box right here. We have micrograms is this one. It means 1/1,000,000th of a gram. Grams is the base unit, and that's the ones with the dashes. It means you only have one of it. And then the micrograms has a multiplier of 10 to the negative 6. So this means that there are 10 to the negative 6 grams in 1 microgram. Remember your box here, this is very important. The multiplier for the micro, the 10 to the negative 6, it goes with the base unit. The base unit is the gram. The prefixed unit, the microgram, gets the 1 when we write out the unit conversion. So again, when using the metric system chart on the back of your periodic table, place the multiplier with the base unit, the gram, and then a 1 with the unit with the prefix. So we'd set it up like this. This is the measured quantity. We're starting with that one here in the first spot. We want to put grams on bottom so that our grams cancel. See my little red line where I'm canceling the grams out. The grams is the base unit. It gets the multiplier, the 10 to the negative 6. Because there's 1/1,000,000th. This means 1/1,000,000th of a gram is equal to 1 microgram. And that makes sense. It would not make sense to switch your numbers there. So then when you multiply across the top and divide across the bottom, we get 3,190 micrograms, or you could write it in scientific notation. This and this, both the way they are written here, are actually appropriate ways of writing it because they both have 3 significant figures. You wouldn't have to put this in scientific notation. 3190 is perfectly acceptable on a test or a quiz. And that's because there aren't very many zeros that either of us would have to count. This problem uses both the metric system and some English unit conversions. So to really make sure your brain understands this process, pause the video to allow your brain to struggle through this problem first before seeing the answer. So in case you were confused with this, the megaliter, the capital ML, that means megaliter, and then a little m would mean milliliter, which we're not using milliliters at all in this problem. So start with the measured quantity, the 5.27 megaliters. First, use the metric system from the metric system chart. We have a multiplier of 10 to the 6. That goes with the base unit, which is liters. And we're going to put 1 megaliter in, on the bottom because we want to cancel our megaliters. From the periodic table, we'd find a unit conversion of 0.946 liters is equal to 1 quart. So you can cancel the liters, put the liters on the bottom. And then we have 4 quarts is equal to a gallon. So you can see all of the units canceled except for the gallons, which is the unit we want to end up with because the question is saying how many gallons. When you multiply across the top and divide across the bottom, and then round it to 3 significant figures because 5.27, this value here, has only 3 sig figs, we get 1.39, times 10 to the 6 gallons. And this one is important to write in scientific notation, not only for the sig figs, but also just because there would be a lot of extra digits at the end that we don't need. Tessa is training for a marathon. She runs 13.5 kilometers every day. How many kilometers does she run in 2.5 weeks? This is a unit conversion problem written as a word problem. We have one unit conversion given in the problem, plus one or two more that we may need to look up on the back of your periodic table. Being able to solve word problems like this with unit conversion setup will help you out for later when we do more complicated chemistry problems in chapters 3 and 4. Pause to see if you can set this up using unit conversions. From the middle of the sentence here, this right here, where it says she runs 13.5 kilometers each day, that is a unit conversion that could be written like this: 13.5 kilometers over 1 day, or the 1 day on top and the 13.5 kilometers on bottom. It will end up either way in the problem, whichever one allows us to cancel the appropriate units we need to. So we already know we have another unit conversion that's 1 week is equal to 7 days. The only number that we're left with then is the 2.5 weeks. That is not a unit conversion. It is an exact amount that we're trying to convert. In 2.5 weeks, how many kilometers can she run? So that's where we're starting off with this measured number. Sort of measured, it's more of a counted number. Well, let's go ahead and use this unit conversion first because it includes the week. This one would not get to cancel anything with the 2.5 weeks. So we put the 1 week on bottom, 7 days on top, and that is how we get to cancel our weeks. And then we have the 1 day on bottom and the 13.5 kilometers on top so that our days get to cancel. Multiply across the top, divide across the bottom, and we get 236.25 kilometers. So maybe this problem seemed a little bit intuitive and you knew which numbers to multiply and you could get this answer without setting up unit conversions. That's fine, but in order to get all of the points on a test or a quiz, you have to show your work setting up with unit conversions, and this is extremely important. For later on, it's not going to be intuitive. The complicated chemistry unit conversions and chemistry concepts, it's not going to be intuitive whether you need to multiply or divide the numbers, so you need to know how to set up the problems. Don't worry about the significant figures for this one because we don't have any measured numbers in this problem. Like I said before, we have exact numbers or counted numbers. The 2.5 weeks is an exact amount, and then we have a couple of unit conversions, and neither of those should ever be considered for significant figures at the end of the problem. So we're not going to round this at all, and that's perfectly acceptable. When you're completing practice problems for 1.6 in your practice problem packet, it is very important that you learn how to use dimensional analysis, which is this factor label method that we just did in the last 4 problems. In chapters 3 and 4 in this chemistry class, we will be doing chemistry problems that will be very difficult to solve any other way other than dimensional analysis. So for right now, you must use dimensional analysis on all of these easy problems, even if you would know how to do it in your head. And this will just make your life so much easier later on.